promise is a promise. Well, with the microphone on now, it's official. Good morning. A promise is a promise. I expect 100% correct answers. You had almost 24 hours to think about it. And survey says two so far. And of course, oops, no. What is happening is, well, in physics, as you know, it's always helpful to draw something, some kind of a picture, a diagram. And I always draw a diagram which helps to understand what is happening. So here we start from a certain amount of water. So water is like a puddle for me. And we're cooling down. So to demonstrate that process, I show some arrow. It represents what is happening to the temperature. And what is the lowest temperature a water, any kind of, in all our problems like cream, milk, soda, we all treat as water, right? So what is the lowest temperature water can reach? Yeah. Zero. Because there is no water below zero. At zero, it starts freezing. So, and this is what we want to end up having solid water, or we call it ice. So there must be a phase transition period. The temperature doesn't change anymore. And then the temperature goes down to -5. And this is a phase transition temperature, special temperature. We know. Where do we find this temperature if we don't know? For example, what is the phase transition temperature for copper? It's solid, but if we heat it up, eventually it starts melting. So there's supposed to be phase transition temperature for copper. Do you know? I don't either. So what do? Yeah, we just do a search. But this substance, water, is so important. So we just remember very important values related to this usually. But they also on the equation sheet. And so how many processes do we see here? 3. This is what we call temperature change, well, TC. This is what we call phase transition. And this, again, temperature change. For each process, we have one equation which describes the amount of heat which is being absorbed or released. And in this situation, it is being released. The freezer takes heat. And by doing that, what does it do? Well, molecules move slower and slower. Eventually, they get closer and closer. That's when phase transition is happening. And eventually, it becomes a solid piece of ice. That's it. But so We can call it process 1, process 2, process 3, and here for each process we can write an expression for the amount of heat related to this process. For the temperature change, the equation is the same. Now, we need to ask a question. What variables should be the same? What variables should be different? Well, water, or we call it liquid water, and ice, or solid water, they have different specific heat capacitance, and the temperature change is different. Now here we have a phase transition, and for the phase transition, the equation is, well, first of all, the magnitude of the heat related to the phase transition is given by this equation, but we need to remember that we need to make a choice of a sign, a plus or a minus. And here where it's important to understand, yes? Yes. I said different, actually.
You didn't say that.
No. So plus or minus. And here the answer depends on what is happening. So if a system is releasing energy, losing it to surroundings, what should we choose? A minus. So all three Q's will be negative, actually. And if we ask how much heat should water release, in that case, the answer usually is the magnitude of the total amount of heat. So technically, this is what we're looking for: magnitude of Q1 plus magnitude of Q2 plus magnitude of Q3. This is how much heat it loses all the way through this process, and the amount of substance, the mass, of course, stays the same. Same amount of water, same amount of ice. So we can start plugging numbers in. First process is related to water, so we got to use this number for specific heat. Now, we need 20 cubes, 5 grams each, so it's going to be 5 times 20, 100 grams, or 0.1 of a kilogram. And the change, well, it's always final minus initial. So what should I write? And if you write, like some people in the past, final -5 minus initial 25. That would be wrong, because you have to write the temperature change related to this particular process. And for this process, the final temperature is 0. There is no water below 0, but initial was 25. Okay, today all lines are too thin. So now, and we need to take a magnitude of this. Plus, well, let's write it as accurate as possible. So this should be 3 times 10 to the 5th for the phase transition. This is how much heat for 1 kilogram is required to make a transition from ice to water, or water ice. Doesn't depend on the direction. And the amount is the same. The number of grams still 100, so 0.1 of a kilogram. Plus, and now the third term, now it is ice. So we got to use values related to ice. same mass as before. And now temperature change, final for ice minus initial for ice. As you can see, inside those vertical bars, all numbers are negative. Yeah? 0 minus 25, negative, negative 5 minus 0. But we're calculating the absolute value of everything. And now you can finish the calculation, and that will give you how much joules should the freezer take away from water to cool it down, to freeze it, and then to cool down that piece of ice to negative 5 degrees. Any questions? Yes?
How do we know that Q2 is negative?
You said that to me, unless you selected one.
So it's just
Exactly. That's the rule. And what do we do to rules? We follow them. That's it. Another example. Please try to sketch like a temperature diagram which would describe what is happening in this situation. So far, we're just calculating the amount of heat related to a specific process or processes. Yeah. But we will have an example for using the heat balance equation, I think right after this problem. Normally I ask a question, how many processes is happening, which means how many Qs should be used. But we're getting slammed by the time. I've been teaching this course for 10 years. This is the first time when every lecture is 80 minutes instead of 90 minutes. So every day we use 10 minutes less than it's been before. It amounts for 3 full lectures all over the course. So that puts some pressure. You can ask, why did it happen? I have no idea. It just happened. And when I realized that, it was too late. Otherwise, these lectures would start at 8:20. That's it. It could have been an easy fix. I didn't expect the next class begin at 10. Normally, All right, so how many processes do you count here? A good number, good as any. So we have here 2 substances initially, right? We have some certain amount of ice, and we mix with a certain amount of water. We know that there is the transition temperature between ice and water, which is 0 degrees of Celsius. Now, theoretically, when we mix ice with water, for example, we may have three different options. The final temperature might be above zero, the final temperature might be below zero, and the final temperature might be is equal to zero. And depending on the situation, our reasoning might be slightly different, but in this situation, the final temperature is what? This is the final temperature. So, what is happening to water? This, what? Yeah, exactly. But something should be happening, otherwise we can't write an equation. So, temperature of water decreases. And actually, what was the initial temperature? 10, right? And how do we call this process in real life? Cooling down, right? Now, and that's it. What is happening to ice? Right now. It starts melting right now. The initial temperature of ice equals negative 10 degrees of Celsius. Of course, it can't start melting until it reaches melting temperature. So at first, it will be warming up to zero. Then it starts melting. Eventually, all ice melts. What we have after that is a puddle of cold water, the water at 0 degrees of Celsius. So what should start happening to that water? If the final temperature is 5, yes? Heating up, yep. It should reach the same temperature eventually. That's how we end up with a large amount of water. One water kind of comes from initial water, which cools down, and second part of it comes from ice being melted. So for each line, we have a Q. Each line represents a process. So how many processes do you see? 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 So if you see 3 processes, please raise your hand. If you see 4 processes, okay, you've changed your mind. That is correct. We see 3 processes for ice, plus 1 process for water. So we have 1, 2, 3, 4 processes. For each process, we have a certain amount of heat released or absorbed. We can call them 1, 2, 3, 4. And now for each process, we can write the equation which represents that amount of heat. For example, Q1 is equal to, well, every time we make the same choice between Cm delta T or L times M. The choice depends on what type of a process is happening. If it's a temperature change, Cm delta T. If it's a phase transition, L times M, or plus or minus. So for Q1, what should we write? Cm delta T. Doesn't matter. So that's water. Water, water, and water. Now, actually, could have been easier count from, doesn't matter. Okay, Q2. Q2, what substance, what process? water changes temperature, but this is a different type of water. The amount of this type of water is different because it comes from ice. So it should be the mass of ice. And delta T, I don't know, just 2. Q3. What equation? Lm plus or minus? Plus. When ice melts, it absorbs the energy. So a plus L M. What type of, which M? Ice. Q4. C of what? Ice. M of ice and delta T, let's say ice, I don't know. As long as we keep them different, that should be fine. Well, now actually we need to assume everything is happening like in a styrofoam cup, no heat exchange with air or something else. Yes?
What is...
It's not T2, it's delta T2. It's the temperature change related to process number 2. I don't know how to call it, because I cannot call it water or ice. Those taken, W and I already taken, so I just call it 2. Well, now, what are we looking for? We are looking for this. We don't know how much water was used. And, well, mixing, yeah. Mixing assumes that the total amount of heat some parts of the system absorb should be equal to the total amount of heat other parts of the system release. So here we can write the heat balance equation. In which form doesn't matter, so let's write it in the most general form, because it doesn't matter. If I need an extra space. All right, so just want to preserve the notations. So C water, M water, delta T water plus, what was it? C water, M ice, delta T2 plus L M ice plus C ice, M ice, delta T ice equals 0. This is our equation, which has a single unknown here. In numbers, okay, so this is 4,000 times what we're looking for, times, it's always final minus initial water. So final is 5, initial was 10, 5 minus 10. Plus water. How much ice did we have? 100 grams. 0.1 of a kilogram. So this is always final minus initial. For the process number 2. For the process number 2. It begins here, it ends there. Final temperature equals what? An initial? So 5 minus 0. Plus the third term. This is latent heat, 3 times 10 to the 5th, times the mass of the ice, plus the last term, specific heat of ice is about a half of specific heat of water, the mass of the ice, times the temperature change for this process. So it begins on -10, it ends at 0. The process ends at 0. So we have to see and understand the difference between the final temperature for the process and the final temperature of the system. The final temperature of the system is 5, but for this particular process, the final temperature is 0. So final minus initial, 0 minus 10. Of course, that's what I was waiting for. Is 0. See, this is a simple equation which, well, you can solve, but I'm not going to do it right now. But what I do the first is just so I see how many zeros I can cross out. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Since the equation is equal to 0, we can multiply it, divide by anything. So it's just easier to cross out all possible zeros and then equation. All right, what equation do we have here? 5 minus 10 is -5. -5 times 4, -20. -20 times mw. Plus 5 times 4 is 20 times 0.12 plus 300 times 0.130 plus minus and minus makes it plus 10 times 0.11 equals 0. So mw equals 33 over 20. 1 point something kilograms. Thank you. Why do we need such a huge amount of water to melt just 100 grams of ice? Because of this number. 300,000 joules we need to spend to melt a kilogram of ice. It's a huge number. It's very unusual. For lead, it was like 100, no, about 1,000 something. So water is a very unusual substance. This is one of things about water. It requires a lot of heat to make a transition, or it releases a lot of heat. Plus, we said yesterday, most objects expand when we heat them up. So when they cool them down, they contract. But water actually, when we start cooling down, when it's getting closer and closer to freezing point, it expands. That's why ice floats above and fish survives underneath. Otherwise, it would freeze all the way down and would kill everything. We don't know why water is so special. It's just a good thing it's so special. All right.
Water freeze if it doesn't have enough room to expand.
Well,
Space,
buy a bottle of beer, put it in the freezer, and wait. What will happen? So it's getting colder and it explodes. So it behaves opposite to other objects. If you take a piece of copper and put in the freezer, it contracts. Well, okay, I'm going to read and draw. We have two objects here put together. And we have some liquid, and we have some solid object. And for the liquid, the initial temperature is 500 degrees of Celsius. And the initial temperature of this solid object is twice of that. How do we know? We can read. Twice of that means 1000 degrees of Celsius. The mass of the solid object is equal to 1/3 of the mass of the liquid. However, specific heat of a solid object is twice of the specific heat of the liquid. Oh gosh, the container. So, the mass of the container is equal to 1/4 of the mass of the solid object, and the specific heat of the container is equal to 1/2 of the specific heat of the liquid in it. And there is nothing said about the initial temperature of the container. That's the initial temperatures. So what would you assume? Well, the standard assumption that a container with the liquid was sitting and waiting until we put something in it. So they have been in thermal equilibrium with each other for quite some time until we placed a third object which is hot, you know. So that means that should be also 500. And we assume that there is no heat exchange with anything else except these three substances. If we make that assumption, that means we need to use heat balance equation, which says, well, what should be happening? We know a cold object should cool down, a cold object should warm up, a hot object should cool down. So, liquid should warm up, the container should warm up, and that solid object added to it should cool down. So we should have 3 Qs. No phase transition is assumed. Otherwise, the problem wouldn't be possible to solve because we don't have information about latent heat, something else. So what do we do now? Since each equation represents temperature change, we write C1 M1 delta T1 plus C2 M2 delta T2 plus C3 M3 delta T3 equals 0. But we need to call them. We need to call something to be number 1, something to be number 2, something to be number 3. So, what do you want to call the object number 1? Container, liquid, or the solid? Liquid. Number 2, that automatically gives number 3 to the container. So now we can rewrite the equation. C of liquid times mass of liquid times temperature change of the liquid, which is final temperature minus initial temperature, plus C of solid times mass of solid times final temperature minus 1000 plus C of container times mass of container times final temperature minus initial of container is equal to 0. I'll try to fit it in here. 0 equals, now we gotta use all our relationships. What do we know? We keep liquid. Okay, let's keep liquid. Final minus 500 plus. Okay, heat capacitance of solid object is equal to twice of this. The mass equals 1/3 of this. For the container, 1/2 of this. Now the mass. That's kind of tricky. The mass of the container equals 1/4 of the mass of the solid, which equals 1/3 of the mass of the liquid. So 1/4 and 1/3 gives 1/12 of the mass of the liquid. That's it. I'm going to stop here because now we can cancel Cm, Cm, Cm. Even we don't know those variables, it's a very common situation. What is good about heat balance equation? Everything equals 0. And now there's only one unknown variable left, final temperature. And you can rearrange and solve it. Okay. I have to start the last part of the last topic, unless you have any questions. Please. Yes?
Why did we assume that the container is 512?
It's a standard assumption, as I said. If you do an experiment like that, you have a container with the liquid which is sitting in a while together. So they should be in thermal equilibrium with themselves. And then you take, usually it's a piece of lead, heat it up, put in it, put a thermometer to measure temperature, and then you use all those data to calculate. Well, usually this type of experiment has been used to find the heat capacity of something, of some material. For example, you know the heat capacitance of liquid and the container, and you're looking for the heat capacitance of that material solid object made of. You measure temperatures and you solve it for C instead of, So it can be done in any way, as long as we measure everything else. We can measure masses because we have scales, right? All right. This is what you know from chemistry. If we look inside everything, every object, we see billions of billions tiny particles, atoms and molecules, and they constantly move. And by now we know lots of stuff. For example, we know that they're very light. The mass, for example, of the oxygen atom, And if we take even a small amount of matter, like 1 gram, inside we're going to have a lot of those particles. So these numbers are not very intuitive, so people have invented better, more intuitive numbers. Physics is just history of inventions. Inventions of things to measure or calculate, that's it. Kinetic energy, it doesn't exist in nature. Someone invented it. Same here. Someone invented the Avogadro's number. Not Avogadro, interesting. This is just a specific number, like a dozen, which is convenient to measure the amount of stuff. The amount of stuff which has this number of particles has a name, a mole. And now we can count the amount of matter using, well, we can count the amount of matter using kilograms or meters cubed, or now we can use moles. 1 mole is the amount of matter which contains 6 times 10 to the 23rd individual particles. So 2 moles, how many particles does it have? Which is 12 times 10 to the 23rd, that's it. And if we take 1 mole of substance, put on a scale, and measure the mass, that's what we call the molar mass. And for molar mass, people use different letters, different textbooks. Sometimes it's a capital M, sometimes it's a Greek letter mu, sometimes even both in the same textbook. So a molar mass is a mass of 1 mole. And for different materials, it's different. This is how we can, one of the ways to calculate it. If we need to calculate the molar mass, we can multiply the mass of a single particle, single atom or molecule, times the Avogadro numbers. That's it. Now, you should know that from chemistry that you can use periodic table to extract the information of the molar mass. For example, for a hydrogen, well, first of all, the hydrogen has 2 hydrogen atoms here. The molecule is diatomic. So if we want to calculate the molar mass, which is the mass of 1 mole, we just need to take the molar mass of a single atom, which is about 1. You can read it there. And multiply by 2. 1 times 2. But what is a unit for this? If you use periodic table directly, it's gram per mole. So 2 grams per mole. Or 2 times 10 to the negative 3rd kilograms. Now, we're going to talk about gas only, starting from now. And we're going to talk about a very special gas, an ideal gas. An ideal gas, a model of the ideal gas, is a set of particles traveling in space without any friction, without any rotation. For now, colliding with each other and colliding with the walls of the container. That's it. Question. So first of all, to contain a gas, we usually need a container. That's what we call it, a container. It contains the gas. So if we have, like, this room filled up with gas, we have billions of molecules traveling with different velocities in different directions, hitting on everything, on walls, on ceiling, on floor, on you, on me. We experience this as a pressure. Theoretically, we can calculate the thing we call average velocity. Average velocity is velocity number 1 plus number 2 plus number 3 plus number 4 plus number billion and 1 plus number 2 billions and second, and divide by the total number. That's what average is. Please keep answering the question. So why is it important? Well, first of all, again, we remember when an object, a ball, or an atom bounces off a wall, it exerts a force. So 1 force, 2 forces, many forces. Force over area, that's a pressure. So clearly, how fast or how slow particles move should be reflected in the pressure the gas exerts. Also, another thing, please keep answering the question. We also know have some energy. Each individual particle has a certain kinetic energy. Some might travel faster, some might travel slower, but we can always, at least theoretically, calculate the average kinetic energy, and that should be positive. Unless suddenly they all stop, which never happens. From classical point of view, it could have happened, but quantum mechanics says they never stop. So technically, kinetic energy is never negative, never zero, it's always positive. So the question is, what do you think about average velocity? Average velocity. What is a velocity? What does it describe? And what properties does it have? What is so special about velocity? What's the difference between, say, velocity and speed? It has a direction. So if you have particles traveling in all possible directions, and you're adding all those vectors, one vector points to the left, second to the right, up, down, this way, that way. And for each short vector directed to the right, there is equally short directed to the left. For each long vector directed up, there is at least one same long directed down, because they travel in all directions. So, if you're adding this plus 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 this, I can keep going and going, plus this, plus, no, vector cannot be bent, plus, what did I do? This, plus this, etc., billions and billions of billions of billions of vectors like that. The result will be equal to what? 0. And what did you say? You said it depends on the temperature. Well, now you know. If it wouldn't be 0, it would mean they travel on average in the same direction. So the whole room would be moving right now, like a balloon. If this average velocity wouldn't be 0, it means the center of mass of the system would be traveling in space. But that's not happening, which is a good thing. Well, now, kinetic energy is used to give an official definition of what we call absolute temperature. So this equation is a definition. Well, one of, sort of, but mostly, yeah, the meaning of this is that's how we defined absolute temperature. To define the absolute temperature, we use a constant, which has a name, Boltzmann's constant. But still, temperature is basically a measure of average kinetic energy. That's it. That's what it is. They travel faster, higher temperature. Molecules travel slower, lower temperature. And we make it absolute related to kinetic energy because it's never 0. So absolute temperature is never below 0. Theoretically, it could be 0. In real life, we can't make it 0. So this is just a definition, a convenient by many reasons. This used to be an exercise 10 years ago. Every student would have to do this exercise to use mechanical approach to derive this equation. I've done it when I was in high school. Because it's kind of very transparent. You just use the Newton's law. One particle bounces off a wall and exerts a certain force multiplied by number of particles, etc., and you get this equation. This equation relates the pressure exerted by a gas, the volume of a container containing the gas, and the same average kinetic energy of a single particle and the number of particles. But now, if we combine these two together, we can write an equation like this. We can replace average kinetic energy. This is much easier because we can measure temperature, we can measure volume, we can measure pressure, but this also is not very convenient. For example, this constant has a negative 23rd. So we just rewrite it using more convenient numbers. This is what we call the ideal gas law. For any ideal gas in a container, pressure, volume, temperature, and the amount of gas measured in moles are related like this. This is a universal gas constant. If you, up to that, you can do some algebra and derive that equation from that equation. It's just a matter of substitution. A universal gas constant is just a product of Boltzmann's constant, which is a part of a definition of absolute temperature, and Avogadro's number, which is basically a part of a definition of mole. And now we can solve a lot of problems. Question: what do you think? So the law, which we're going to use now, relates a pressure inside the container, the volume of the container, the temperature, absolute temperature of the gas, the number of moles, and this is just a constant. So I can do some algebra. For example, I can rearrange this expression, and this fraction PV over NT should be equal to 8.31 for any gas, at any temperature, at any pressure, in any volume, always constant. But that's not I'm asking you about. I'm asking you about this. What do you think about this ratio? Would it be always constant? Sometimes constant. Always change depending on the gas or circumstances, or maybe something else. Well, the answer is, of course, this ratio depends on the amount of gas. So when the amount of gas changes, this ratio changes. When the amount of gas doesn't change, this ratio doesn't change. That's it. How can we change the amount of gas? We can drill a hole in a container and let it out, for example. So why is it important? Because people sometimes, you think that this ratio is always constant and apply it to a situation when amount of gas changes, and that will not work. So let's do an example. First, when the amount of gas does not change and one of the other variables remains constant, we have a process which has a name. And names are important because if you read the problem, it says like isobaric process or isochoric process. You need to know what it means. This is what it means. Isobaric process is a process which is happening at constant pressure. The example of this process. Well, I can move it by adding some pressure, but instead of actually doing work by my hand, using my muscles, I just put it in hot water. So the volume changes, the temperature changes. It's getting hotter, the volume increases. But if it travels relatively slowly, the pressure is balanced by the weight, and the weight is the same, constant. So the pressure remains constant. Now, isochoric, Greek words. This, if we have a, well, we call it a pressure bulb. You know, again, we can put it in hot water. The volume is fixed by basically the volume of this bulb. So the volume remains constant. What changed? Temperature and pressure. Temperature goes up, pressure goes up. If temperature goes down, the pressure goes down. And oops. One more process, isothermal. It happens when we change very slowly volume and pressure. Here I have a syringe, and I can change the volume by pressing in. Oops. Are you broken? Okay. Let's try it opposite way. All right, this one is broken. I'm going to show you tomorrow. I'll fix it. But when we compress, the gas decrease the volume, we increase the pressure. If we do it fast, that wouldn't be the isothermal process. Because if I move a piston quickly, it hits on the molecules and make them move faster, so the temperature would change. So we really have to do it slowly. If we do it slowly, so the temperature inside of the syringe balanced out quickly with the outside temperature, and that means we observe the isothermal process. And these equations has been derived from experiments more than 100 years ago. Boyle and Marriott, Sherrill, Gay-Lussac. Now we can just apply ideal gas law, well, first of all, again, for each iso process, we assume that the number of moles is conserved. We don't change it. Otherwise, it wouldn't work. So if this is constant, n is constant, and another variable is constant, that means, for example, if pressure is constant, V over T should be constant. If the volume is constant, P over T should be constant. If the temperature is constant, the product, P times V, should be constant. All comes from single law. That's not a question. Let's just do it quickly. An ideal gas starts from a certain temperature, and we change something, we change pressure, and some amount of gas is lost. So what is happening? We start from initial values. We end up with some final values. What we know is, no matter well, I don't like fractions, so I write the law in a standard form. Some people like use a fraction. And the same law, the same equation we can write for the second situation. What can we do now? Ratio. P1 V1 over P2 V2. No cheating. That's what it should be equal to. Well, first of all, oh, sorry. First of all, we can cross R's. Now we can start using information given to us. Well, initially P1, V1, and 1. And the only number we can read here is initial temperature. Can I write 127? Why? It has to be kelvins, exactly. So T1 should be equal 127 plus 273, 400, right? Kelvin. Now, the volume was tripled. The pressure was decreased to the half of the initial. And a quarter of a gas was lost. I have a question mark here because I need your reaction. Yes? Why? Exactly. So that is how we have to proceed. We're looking for something what is happening inside. So every variable we use is supposed to be related to the gas inside of that container. So technically, this is what we can write. We had a certain amount and we're losing, we're subtracting a quarter of that. So that's how we know that 3/4 should be left inside. So 3/4. And that's what we're looking for. And as you can see, again, P1 and P1 canceled, V1, V1, and 1, 1, 1, and we solve it for temperature. Energy. We know that in general, an object might have two types of energy, translational and rotational. So does molecules. If a molecule is actually just an atom, we call it a monatomic gas, like helium. So those molecules can only travel in space, they can't rotate practically. But if we have a hydrogen molecule, H2, it has two atoms. And this molecule can travel in space, but also it can rotate about two different axes. Rotation about this axis doesn't matter. We should imagine that it's actually tiny, not a big thing. So this matters, this matters, this axis doesn't matter. And if we have three atoms or more, in that case, of course, they can travel in space and they can rotate about three independent axes. So that affects kinetic energy. For a monatomic gas, kinetic energy is equal to just regular mv squared over 2, translational energy, for a single molecule. If we want to calculate the energy of the gas, we just need to multiply by the number of particles. And that's what we call the internal energy of the gas. And for a helium or any other monatomic gas, the internal energy, if we work it out, is equal to 3/2, number of moles constant, and temperature. Increase in temperature, more internal energy. Decrease in temperature leads to less of internal energy. But if we have a molecule, rotation also provides some energy. For a diatomic, we should add energy related to rotation about 2 additional axes. So for a diatomic gas, this is how we calculate internal energy, not 3/2, 5/2. This number has a name, the number of degrees of freedom. It has 5 degrees of freedom, x, y, z. Rotation number 1, rotation number 2, 5. And all other gases, CO2, for example, or something more complicated, they have 6 degrees of freedom, x, y, z, first axis of rotation, second axis of rotation, third axis of rotation. So the total internal energy of a, well, we call it polyatomic gas, is equal to this. And of course, we just write one equation for all situations. This variable I has a name, the number of degrees of freedom, and it is equal to 3 for a single atomic monatomic gas. It equals to 5 for a diatomic gas, and 6 for all other gases. Now, we know the equation for the gas, and now we know the equation for internal energy. We can put it together. This is another, sometimes more convenient equation for internal energy. Most commonly, we're not looking for the energy, we are looking for the change. So this is how we can calculate the change. We can use either this equation or that equation. It depends on what variable remains constant. For example, if the pressure is constant, this is how we can calculate the change. Because P is constant, only volume changes here. When the volume is constant, this is also how we can calculate the change. Because if the volume is constant, only pressure changes. If the temperature is constant, there is no change. Even if volume and pressure both change, the original equation tells us when temperature remains constant, internal energy doesn't change. Well, that completes almost everything you need to know for this homework. Let's do some examples. Hydrogen gas. So first of all, we need to remember it's H2. So the molar mass equals 2 times 10 to the negative 3 a kilogram over a mole. Which means if we have 1 kilogram of this gas, the number of moles, which is this, should be equal to 1 over 2 times 10 to the negative 3, which is equal to 1,000 over 2, 500 moles. That's actually a huge number, not very regular. And, well, room temperature. Room temperature is about 20 degrees of Celsius, 30 degrees of Celsius. Let's call it 27 degrees of Celsius. In that case, the absolute temperature will be 27 plus 273, 300 Kelvin. So, pressure, nRT over V, nothing special here, 500, about 8, I'm going to round it up, temperature 300, 1 liter. Can we use 1? No. We need you to use cubic meters because all units here belong to international system of units. 1 liter, 10 to the negative third, 1,000th of a cubic meter. That's the pressure in pascals, a huge amount of pressure. What about energy? Well, we can use either equation, but we need to remember this is a diatomic gas, H2. So we have to select a 5 for the number of degrees of freedom. Sorry. 500, 8, 300. That's going to be joules. I'm going to finish at these numbers later. Don't answer this question. The answer is 0. When temperature initial equals temperature final, the temperature change equals 0. Hence, the temperature doesn't change, internal energy doesn't change. We can see it from this equation. And that's what we need to do always. We have to choose the equation which provides most of the visible information. Yeah. This wouldn't help to see it immediately. Well, calculate the change if the gas expands. All right. Now, you see what I see? I see that I know the initial volume and I know final volume. And I know that the pressure is constant, which means initial and final pressure is the same. So I have a lot of information about the volume and the pressure. That means this is the equation I want to use. Delta U should be equal to still hydrogen. Pressure remains constant, kilo pascals. And the volume changes. Final minus initial. Final is 7 liters. 7 times 10 to the negative 3. Initial is 3 liters. 3 times 10 to the negative 3. Cubic meters. 1 liter is 10 to the negative third cubic meter, which has been found before a couple of times. If you look at the units here, kilos and liters, they actually cancel each other out. Sometimes it's a convenient shortcut. So all we have to calculate I have 1 more minute, times 4 joules. Well, it's an ironic that the song says never gonna stop me and I have to stop. Oops. You know what to do, right? Good morning. This one is broken. You can put it away and we should have another one. I will check this tomorrow. But there is one, I think, on the table.
Can I take it down?
Yes. Yes.
For next summer session's physics class, I was wondering if it was possible to change a lab section into one that was already full. Because I teach.
Oh, you mean you want to switch in the lab section?
Yeah.
That we can talk when it begins.
Okay.
Okay.
Only reason is because I teach a Bio 108 class, and it's actually during the time that I had signed up for.
What do you teach?
Bio 108? The introductory biology course. But it's
Well, first-
during the time that I signed up for. So
You should send me an email anyway, but normally one or two switches shouldn't be a problem.
Okay.
But
send
we
you
have
an
to,
email.
yeah, but officially we can talk about it when it begins.
Got it. Thank you.
In this problem, how do you know that the temperature changes versus the last problem where we knew that it was going to be zero energy change? Because it doesn't say anything about the temperature.
I don't even care in this problem.
Okay.
But it does change
Okay.
because if you have a question?
Yeah, but I can wait.
Okay. So the question here is about U, internal energy. And we know that when pressure is constant, and the number of moles are assumed to be constant, these variables related,
They have to change together.
they have to change together.
So we know that temperature changes this one. Okay.
Yep.
All right. Understood. Thank you.
Yes.
I have a question. I was in class yesterday, but I left right after. And was there sign-in?
Yesterday it wasn't.
It wasn't. Okay. I just want to make sure I didn't miss it. And then I can't remember if I missed